Welcome to day 6 of our Python data science journey. I'm excited to guide you through what might be the most practical and hands-on lesson yet. Today, we're going to transform raw data into actionable insights using Python's most powerful libraries. By the end of this session, you'll have built your first complete machine learning model. Before we dive in, I want to introduce you to an amazing free resource from Google called Colab. Instead of wrestling with installations on your local machine, we'll use Google Colab, which comes with everything pre-installed, including its own AI assistant called Gemini. You can follow along with today's lesson both here and in my shared Colab notebook, where you can see the code and results in real time. Feel free to copy it to your own account and experiment. Let me show you our roadmap for today. Here's what we're going to build together today. We're creating a comprehensive data analysis pipeline step-by-step that covers the entire data science workflow from start to finish. First, we'll master data loading by reading CSV files and exploring dataset structures. Then we'll dive into data cleaning, handling those pesky duplicates, missing values, and data type conversions that every data scientist encounters. Next, we'll create stunning visualizations using Matplotlib, Seaborn, and Plotly. We'll perform statistical analysis with hypothesis testing using t-tests. And finally, we'll build and evaluate a regression model to predict house prices. This isn't just theory, folks. We'll be working with real California housing data and building a predictive model that could actually be used in real-world applications. So let's get started. First, we need to install all the required libraries. Here's the complete list of what we'll be importing today. For data manipulation, we'll use pandas. Think of it as Excel, but supercharged with programming capabilities. We'll use it for loading, cleaning, and transforming datasets, handling data validation, removing duplicates, and managing missing values. For numerical computing, we'll use NumPy for mathematical operations and array manipulation. It's the foundation that makes everything else possible. For visualization, we have 3 powerful tools. Matplotlib for creating publication-quality static charts and graphs. Seaborn for beautiful statistical visualizations with minimal code. It makes complex plots incredibly easy. And Plotly for web-ready interactive charts and dashboards that your users can actually interact with. For machine learning, we'll use scikit-learn to build and evaluate predictive models. And for statistical testing, we'll use SciPy for hypothesis testing and statistical analysis, including R-squared calculations, coefficient interpretation, and performance metrics. Now let's start with step 1, data loading and initial exploration. This is where every data science project begins. Most real-world data science projects start with loading data from external files, typically CSV files. Let me show you how this works. In this example, I'm simulating CSV data that represents product information. In a real project, you'd simply use pandas.read_CSV with your file name. Notice how we're creating a file-like object from our string data and then reading it with pandas. This gives us a data frame, pandas' primary data structure. When you run this code, you'll see confirmation that the data loaded successfully, along with the dataset dimensions. Before analyzing any data, you should always explore its structure first. This is like getting to know your data before you start working with it. Here's how we do initial exploration. We use .head to display the first few rows, check the dataset dimensions with .shape, and use .info to get data types and missing value information. These 3 methods will tell you almost everything you need to know about your dataset structure. Here's what that output looks like. You can see our product data with product IDs, names, prices, and launch dates. The dataset has 8 rows and 4 columns, and we can see that the launch_date column has 1 missing value. Remember these key exploration methods. .head shows the first rows, .shape gives you dimensions, .info provides data types and memory usage, and .describe gives statistical summaries for numerical columns. Now we move to step 2, data cleaning and preparation. This is often the most time-consuming part of any data science project, but it's absolutely crucial. Real-world data often contains duplicates that can seriously skew your analysis. Let's see how to handle them. First, we check for duplicates using the duplicated method, then remove them with drop_duplicates. Notice how we use inplace equals true to modify the original data frame rather than creating a copy. In our example, we found and removed one duplicate row. Clean data is essential for accurate analysis. Missing data is inevitable in real-world datasets. Here's how to handle it strategically. We first identify missing values using ISNA, then decide on a strategy to fill them. In this case, we're filling missing launch dates with the most common date in our dataset. There are many strategies for handling missing data, and your choice depends on the context. After filling, we confirm that all missing values have been handled. This step is crucial. You don't want surprises later in your analysis. When dealing with missing values, you have several strategies. For numerical data, you might use the mean, median, or mode. For categorical data, use the mode or create an unknown category. For time series, consider forward filling or interpolation. And for critical data, you might choose to remove rows with missing values entirely. Data type conversion is another crucial step. You need to ensure your data has the correct types for proper analysis. Here, we're converting string dates to actual datetime objects. This allows pandas to understand that these are dates, not just text strings, which enables date-specific operations and analysis. Notice how the data type for launch_date changed from object to datetime64. This seemingly small change unlocks powerful date and time analysis capabilities. Step 3 is data aggregation, where we transform and summarize our data to reveal patterns and insights. Creating new features or aggregates often reveals hidden patterns in your data. This process is called feature engineering. Here, we're extracting the month name from our launch date and then grouping by month to calculate average prices. This type of aggregation often reveals seasonal patterns or trends that weren't obvious in the raw data. Our aggregation reveals interesting patterns in product pricing by month. This kind of insight could inform business decisions about when to launch new products. NumPy provides powerful array operations that are essential for numerical computing in data science. Here we create a random 3x4 array and demonstrate key NumPy concepts. We examine the array's shape and data type, perform array slicing to extract subsets, and apply mathematical functions like square root across the entire array at once. This output shows NumPy's power. Notice how we can apply the square root function to the entire array in one operation. This is called vectorization, and it's much faster than processing each element individually. These NumPy concepts are fundamental. Broadcasting allows operations on arrays of different shapes. Vectorization lets you apply operations to entire arrays at once. Slicing uses the start, stop, step syntax to extract subsets. And universal functions provide mathematical operations optimized for arrays. This visual demonstrates NumPy array operations in action, showing the original array, slicing operations, mathematical functions, and array arithmetic. Now we reach step 4, data visualization mastery. This is where your data really comes to life. Matplotlib is your go-to library for creating publication-quality static visualizations. This code creates a professional bar chart showing average product prices by launch month. Notice how we set the figure size, add colors, include proper labels and titles, rotate the month labels for readability, and add a grid for easier value reading. The resulting chart clearly shows the price variations by month. April and May have the highest average prices, while February shows the lowest. This kind of visualization makes patterns immediately obvious. Here's what that professional bar chart looks like. Notice the clean styling, clear labels, and the grid that makes it easy to read the values. For Matplotlib success, remember to set appropriate figure sizes, use descriptive titles and axis labels, apply consistent color schemes, add grids for better readability, and rotate labels when needed to prevent overlap. Seaborn is perfect for exploring statistical relationships in your data with beautiful, professional-looking plots. Here we're creating a regression plot using the California housing dataset. This shows the relationship between median income and house values. Notice how Seaborn automatically calculates and displays the regression line and confidence interval. This regression plot reveals a clear positive correlation. As income increases, house values tend to increase as well. The scattered points show individual data points, while the red regression line shows the overall trend. The shaded area represents the confidence interval, indicating our uncertainty about the exact relationship. Here's the beautiful regression plot that Seaborn creates. You can see the clear relationship between income and house values, with the regression line and confidence interval automatically calculated and displayed. Seaborn's advantages include automatic statistical calculations like correlation lines and confidence intervals, beautiful default color palettes, easy categorical data handling, and seamless integration with Pandas data frames. Plotly creates web-ready interactive visualizations that users can actually interact with. This code creates an interactive scatter plot that's essentially a map of California housing data. We use longitude and latitude for positioning, color code by house values, size the markers by population, and include hover information. The result is a rich, multi-dimensional visualization. This interactive map shows California housing data with multiple dimensions simultaneously. Geographic positioning creates a map-like view. Color intensity represents house values. Darker means more expensive. Marker size shows population, and you can hover over points to see exact values. The pattern clearly shows expensive coastal areas like San Francisco and Los Angeles versus more affordable inland regions. In the actual interactive version, you could zoom into specific regions, pan across the state, and hover over points for detailed information. Another great feature of Plotly is easy web deployment for integration with web applications. Step 5 brings us to statistical analysis and hypothesis testing, where we move beyond description to actual statistical inference. The independent t-test helps us determine whether two groups have significantly different means. This is fundamental to data-driven decision-making. Here we create two sample groups with slightly different means and perform an independent t-test. The test gives us a t-statistic and a p-value, which we use to determine if the difference is statistically significant. In this example, our p-value is essentially 0, which means the difference between our groups is highly statistically significant. This would be strong evidence that the groups are genuinely different, not just due to random variation. Understanding these statistical concepts is crucial. The t-statistic measures the difference between group means relative to the variability within groups. The p-value tells us the probability of observing this difference by pure chance. We typically use a significance level of 0.05, meaning we accept a 5% chance of false positives. Our null hypothesis assumes no difference between groups. Now we reach step 6, machine learning and predictive modeling. This is where we build models that can make predictions about new, unseen data. We're going to build a regression model to predict California house values based on various features like income, house age, and location characteristics. First, we define our features. These are the variables we'll use to make predictions. Then we define our target variable, what we want to predict. Next, we split our data into training and testing sets. This is crucial because we need to test our model on data it hasn't seen during training. Our dataset splits into over 16,000 training samples and about 4,000 testing samples. This 80-20 split is standard in machine learning. Now we train our model to learn the relationship between our features and house prices. We create a linear regression model, train it on our training data, make predictions on our test data, and evaluate performance using the R-squared score. We also examine the model coefficients to understand how each feature affects house prices. Our model achieves an R-squared score of about 0.51, meaning it explains 51% of the variance in house prices. That's actually pretty good for a simple linear model. The coefficients tell us that median income has the strongest positive effect on house values, while house age has a small negative effect. When evaluating models, remember these key metrics. R-squared shows the proportion of variance explained. Higher is better. Coefficients show how much each feature impacts the prediction. Mean squared error measures the average squared difference between predictions and actual values. And cross-validation provides more robust evaluation using multiple train test splits. Let me show you now a comprehensive dashboard summarizing all our Day 6 analysis results. This results summary dashboard brings together everything we've accomplished today. It shows our data cleaning progress from 8 original rows to 7 clean rows after removing duplicates and handling missing values. Our model performance with an R-squared of 0.51, meaning we explain 51% of house price variance. The bottom left chart shows the feature importance analysis. We have found that median income has the strongest positive effect. And in the bottom right chart, our statistical test results showing significant differences between groups. This dashboard demonstrates the power of combining multiple analytical approaches, cleaning, visualization, statistics, and machine learning to gain comprehensive insights from data. Let me summarize the complete workflow we've covered today. Here's our complete data science workflow visualized as a process flow. We start with data loading, move through exploration and cleaning, perform feature engineering, create visualizations, conduct statistical analysis, build machine learning models, evaluate their performance, and finally deploy our insights. Here are the key takeaways from today's session. Always start with exploration. You need to understand your data before analyzing it. Clean thoroughly by handling duplicates, missing values, and data types. Visualize everything because charts reveal patterns that numbers alone cannot show. Test your hypotheses using statistical methods to validate assumptions. Build iteratively by starting simple and adding complexity gradually. And always evaluate rigorously by testing your models on unseen data. Now that you've mastered these fundamentals, here's some advanced topics to explore next. Consider diving into feature selection for choosing the most important variables, cross-validation for more robust model evaluation, ensemble methods that combine multiple models for better performance, deep learning with neural networks for complex pattern recognition, time series analysis for data over time, and A/B testing for experimental design and business decisions. Before we wrap up, let me share some practical tips for data science success. Here are the best practices that will serve you well in your data science journey. Document everything using comments and markdown cells. Use version control with Git to track your changes. Ensure reproducible analysis by setting random seeds and saving intermediate results. Develop domain knowledge to understand the business context behind your data. And always consider ethical implications, being aware of bias and fairness in your models. Also, be aware of these common pitfalls that can derail your projects. Avoid data leakage by never using future information to predict the past. Watch out for overfitting where models memorize rather than generalize. Remember that correlation doesn't imply causation. Ensure your data represents the population you're studying to avoid sample bias. And don't ignore outliers because extreme values can significantly impact your results. And that brings us to the end of our comprehensive data science journey. Congratulations! You've just completed an intensive journey through the essential data science workflow using Python. You now have the practical skills to load and explore any dataset, clean and prepare data for analysis, create compelling visualizations that tell stories, perform statistical hypothesis testing to validate your assumptions, build and evaluate machine learning models, and interpret results to communicate meaningful findings. These skills form the foundation of modern data science and will serve you well whether you're analyzing business metrics, conducting academic research, or building artificial intelligence applications. The key now is to keep practicing with different datasets and gradually tackle more complex problems as you build your expertise and intuition. Remember, data science is both an art and a science. The technical skills you've learned today provide the tools, but developing intuition about data and learning to ask the right questions, that comes with experience and practice. Every dataset has a story to tell, and now you have the skills to uncover those stories. Thank you for joining me on this journey through Python Data Science Essentials. I hope you feel empowered and excited to apply these skills to your own projects. Whether you're analyzing sales data for your business, exploring research questions, or building predictive models for decision-making, you now have a solid foundation to build upon. Keep experimenting, keep learning, and most importantly, keep asking curious questions about the data around you. The world is full of data waiting to be explored, and you now have the tools to explore it. Until next time, happy analyzing, and remember, every expert was once a beginner. You're well on your way.